So an ellipse is the locus of all points whose sum of distances to two fixed points, called foci, are the same for each point on the ellipse. So an ellipse is the locus of all points whose sum of distances to two fixed points, called foci, are always the same. So this sum, so if I take the distance from this focus to this focus, passing through a point, it will always be the same for any point on the ellipse. So this distance from here to here and back, from here to here and back, is always the same. So if you start at one focus and you to go to the other focus, it'll always be the same distance. The midpoint of the foci is called the center of the ellipse. So the midpoint of these foci is called the center of your ellipse. The line segment connecting 2 points on the ellipse and passing through the foci is called the major axis. Sometimes I'll call it the focal axis or the real axis. And the endpoints are called vertices. And so this line segment passing through the foci is called the major axis, and these endpoints are called vertices. The line segment connecting 2 points on the ellipse perpendicular to the major axis at the center is called the minor axis or the imaginary axis, and the endpoints are called vertices. So if I take a line perpendicular to the major axis passing through the center, then this is called the minor axis, and these endpoints are called vertices. There's also a bounding rectangle, but we usually don't say much about the bounding rectangle, for ellipses at least. We do for hyperbolas. So where would you see these? If you, say, are the Earth and you're orbiting around the sun, then the Earth goes in an elliptical orbit around the sun, where the center of the sun is at one of the foci of this ellipse. So if you have any celestial object that is in a fixed orbit around another object, then they go in an elliptic orbit, elliptic path, or circular path. Very unusual for circular, but an elliptic path, where where the center of what you're orbiting lies on one of the foci of the ellipse. If you are in a whispering room and you are located at one point and your friend is located at another point, a whispering room is an ellipsoid. It's a room that looks like an ellipsoid. It is elliptical in all sort of, think of it as, and so if you, well, of course, usually it cuts it off because you want to walk around. So it's half an ellipsoid. It should be a full ellipsoid, but then you'd be suspended, so you can't really have a full ellipsoid. But a whispering room is such that if you're located at these points and you whisper, then the person, and it doesn't matter how far away they are, can hear you as if you're whispering inside their head. And so some of these rooms are, like 100 feet apart, 200 feet apart, where you whisper to someone, they can hear you, but the person 5 feet from you can't hear you, but the person 100 feet away can still hear you. So it's kind of weird. Next, suppose you have a kidney stone, and so one of the treatments for a kidney stone is that they put you into a bath of water, and they vibrate the edge of this which we'll call it the edge of this bath, and if your kidney stone is located at a at the focal point, then it gets destroyed, and that's what it's called. It's called, and then it passes through you. So I'm just sort of looking up what it's called. It is called extra corporal shockwave lithotripsy. So that's what it's called. That's a treatment where they just put you in a bath, and a bath of water or whatever, and basically all the energy is focused on your kidney stone, and it's destroyed. Okay, so let's derive an equation of an ellipse. First, let's simplify this. So let's suppose that that the center is at the origin, and let's say that the vertices are the foci are located at C0 and minus C0, and let's say that the two vertices are at A0 and minus A0, and suppose that these vertices are at 0B and 0 minus B. Okay. So first, let's look at, I guess let's look here. Let's take this point here and find the equation, find the distance from this point, this vertex, to each of these foci, and then add up those. So let's start at, so let's first consider the distance from the vertex A0 to each of the foci, minus C0 and C0. Well, the distance here for this one is going to be A, because that distance here is A plus C. Let's look at this other distance. Well, this is A minus C gives me this distance. So if you took away from AC, that distance is this here. So it's A plus C plus A minus C. C's cancel. So you just get 2A. So since I know that the sum of the distances on an ellipse is always constant, that means that I'm going to use the fact that the sum is always equal to 2A. Okay. The sum is always going to be the major diameter. Okay, so next, let's figure out the distance here using this point here. So start at this focus, go here, and then there. Well, the distance formula, which we had from before. So we call the distance formula between the points P and Q is just the square root of the sum of the squares of the differences of the x and y coordinates. So let's consider the distance from this vertex on top to each of the foci. So I'm going to go from here to here. So this distance plus this distance. So it's going to be from 0 minus the negative c, so 0 plus c squared plus b minus 0, b squared. So square root of b squared plus c squared. And then do this distance. Well, c minus 0 squared, so that's c squared. B minus 0 squared, well, that's b squared. So the square root of b squared plus c squared. So I get that the distance is the sum of the square root of 0 plus c squared plus b minus 0 squared plus the square root of 0 minus c squared plus b minus 0 squared. And so since the sum is always equal to 2a, I know that each of these are radical b squared plus c squared must equal 2a. So canceling out the 2's, squaring both sides of my equation, I get that a squared is b squared plus c squared. And so I have that b squared is a squared minus c squared. So we'll be eventually using that fact. So now let's consider the distance from the point P, X, Y to each of the foci, negative C0 and C0, and use the fact that the sum of the distances to the vertices is always equal to 2a. And so square the distance from xy to minus c0 is x, the square root of x minus a negative c, so that's x plus c squared, plus y minus 0, quantity squared, plus, let's find the distance between this point and this foci. So the square root of x minus c squared plus y minus 0, quantity squared, equals 2a. Okay, so this is just y minus 0 is just y. Y minus 0 is just y. Let's try to solve this. So let me subtract radical x minus c quantity squared plus y squared from both sides of my equation. And so to solve this radical equation, I isolate one of the radicals on one side of my equation and then square both sides of my equation. And so the square gets rid of the square root. So I just get x plus c quantity squared plus y squared equals. Now let's use a special product formula to simplify this. So I get 2a quantity squared is 4a squared minus 2a times radical times 2 is a minus 4a times the radical x minus c quantity squared plus y squared. Plus, well, the square gets rid of the square root, so plus the y minus c quantity squared plus y squared. The y squares cancel. Let's simplify this by the special product formula, the perfect square trinomial. This is just x squared plus 2cx plus c squared. Let's rewrite the first two terms. 4a squared minus 4a times the radical x minus c quantity squared plus y squared plus. Now, let's multiply out the x minus c quantity squared. So by the special product formula, the perfect square trinomial, I just get x squared minus 2cx plus c squared. X squares cancel, c squares cancel. Let's add 2cx to both sides of my equation. So 2cx plus 2cx is 4cx. Subtract 4a squared from both sides of my equation. So I get that 4cx minus 4a squared is just this quantity remaining, the minus 4a times radical x minus c squared plus y squared. Divide both sides of my equation by negative 4. So negative 4a squared becomes positive a squared. The positive 4cx becomes a negative cx. Square both sides of my equation. And so by the special product formula, a squared squared is a to the fourth. A squared times minus 2cx times 2 is a minus 2a squared cx. Square the last term, plus c squared plus x squared equals, well, a squared is a squared. The square gets rid of the square root. Let's simplify x minus c quantity squared using the special product formula, the perfect square trinomial. X squared minus 2cx plus, well, square the last term, c squared plus y squared. Let's multiply a squared inside the parentheses. And so, just rewriting the left-hand side of the equation, a to the fourth minus 2a squared cx plus c squared x squared equals a squared x squared multiply minus 2a squared cx multiply plus a squared c squared multiply plus a squared y squared. The minus 2a squared cx's cancel. Let's subtract a squared c squared from both sides of my equation. So I get a to the fourth minus a squared c squared. Factor out a squared. So it's a squared times a squared minus c squared is equal to, well, it subtracts c squared x squared from both sides. So I get a squared x squared minus c squared x squared. Factor out your x squared. So we get a squared minus c squared times x squared plus, well, this last term, a squared y squared. Now, recall at the very beginning, I said that b squared was a squared minus c squared. So let's replace a squared minus c squared by b squared. So this becomes a squared b squared equals b squared x squared plus a squared y squared. Divide both sides of my equation by a squared b squared. So dividing by a squared b squared, well, the b squareds cancel, x squared over a squared plus divide by this term by a squared b squared. The a squares cancel, so you get y squared over b squared equals, well, the a squared and b squareds cancel here, so it's equal to 1. So this is the equation of my ellipse. This is the equation of ellipse centered at the origin, where the distance to the each vertex, well, in the x direction is a and the y direction b. So if I translate, and I also have the fact that b squared is a squared minus c squared. Now, I use the fact that a was bigger than c, that a was along the focal axis. Now, I don't have to actually assume that. I can just say, well, let b squared equal a squared minus c squared. If I do that, then this equation is valid even if the focal axis were along the y-axis. And nothing really changed, the sign that changed. Okay, so next, let's translate. So suppose I have an ellipse where the center is at hk, the vertex is at h plus or minus a, k, h, k plus or minus b, and the foci is at h plus or minus ck if a is greater than b, and h, k plus or minus c if b is greater than a. I have here that I wrote it this way. Okay, doesn't really matter. That's c squared equals a squared minus b squared. Okay, so you could have solved this guy for c squared. You would have gotten a similar thing. Okay, so maybe I'll write it that way. So it's those conditions are the same, but to be a uniform condition, I'll write it that way. Then the equation of my ellipse is just x minus h quantity squared over a squared plus y minus k squared over b squared equaling 1. So let's do some examples. Page 864. Write an equation in standard form of the ellipse described above. The center of each ellipse is the origin. So I'm assuming it's the origin. I have a focus at 0, 4 and a vertex at 0, 7. So suppose I have an ellipse where the vertex is at 0, 7 and the focus at 0, 4. Of course, I know that you'll also be here at negative 4 and negative 7. That I know. I don't know what A is. So this is, I can figure out B from here. I won't know A, so A will be something. I don't know what that is yet. Okay, so I want to determine the equation of this. Well, I know if it's centered at the origin, then the equation always looks like this. X squared over a squared plus y squared over b squared is 1. Okay, so that's easy. I know what a is. I don't know what a is, sorry. I know what b is. B here is 7. The distance from the center to a vertex in the y direction is 7. I know what C is. C here is just the distance from the center to a foci, and so that's just going to be 4. Well, I know that c squared equals the bigger, which is b squared minus a squared. I don't need absolute values here. Why? Because I know the focal axis is along the b-axis. So I know that b is bigger than a. And so I have that 4 squared equals 7 squared minus a squared. So a squared equals 7 squared minus 4 squared. 49 minus 16. And so I have that a squared is equal to 33. And so the equation of my ellipse, let's go one more, over a squared plus y squared over b squared equaling 1. And that is the equation of my ellipse.
I got a question.
Sure.
For B, what would have happened if I would have chose -7?
I'm sorry, you faded out completely.
Oh, sorry. I said for B, what happens if I chose -7?
Oh, what's -7 squared?
Oh, +49. Oh, so that
Yeah,
wouldn't matter then.
it
Okay.
wouldn't matter, but we always let it be the positive one.
Okay.
So I always let A and B be positive. Why? Because it doesn't make any difference, and positive is easier to deal with.
Yeah,
so
I
so we
understand.
just always let them be positive.
Okay.
So that's always it's like the rate with the radius, right? You could say the radius is a -2. It wouldn't make any physical sense, but it would still satisfy the same equation. So we always say that it's positive.
Okay.
Okay. Because we really want them to be a distance.
Yeah. Okay. Thank you.
Okay. Problem number 34. Graph, okay, here it is. I'm sorry, graph the ellipse. Okay, so we want to graph this ellipse. So I know from here that this is an ellipse with a center at the origin. I know that A here is 6, B here is 5. Again, I'm taking the square roots of 36 is 6, square root of 25 is 5. Next, C, 25, I'm sorry, 36 minus 25. So this is a plus sign, so subtract. So think math is always backwards. So you just take 36 minus 25 is 11. And so C is radical 11. So, oops, let me put a little page here. Okay, so now I have that the vertices, well, let's look at the vertices. Are they going to be at plus or minus 6, 0, at 0 plus or minus 5? The foci, 6 is bigger than 5. Therefore, the focal axis, the major axis, will lie along what A is, which I'm always using that for X. So they'll lie along the x-axis, right? Plus or minus radical 11. Now let's try to draw this. In your drawing, you'll not actually use the fact that the focus is at these points, but you really look just at the center and the A and B, the vertices. So the center is at the origin. I go 6. Let's see if I have it. Well, let's see. 1, 2, 3, 4, 5. Good. 1, 2, 3, 4, 5. Good. 1, 2, 3, 4. Okay, come on, get back. 2, okay, come on. 3, 4, 5, 6. 1, 2, 3, 4. Come on. 5, 6. Okay, so my ellipse, if I can do it. Yeah, whatever. Okay, so good enough. So my center is at the origin. My vertices, so this is 5. 0, 5. 0, -5, and that's 6. 6, 0, minus 6, 0. And square root of 11 is a little over 3. So let's say this is 2, 3, the foci. So here are the foci, the center, and the vertices. And that's what my ellipse looks like. Of course, this is my, actually maybe I'll, major axis, and this is my minor axis. Okay. Okay, so that is what your ellipse looks like. Problem 43. Okay, so before I can do this, graph this, I first have to put it into a standard form. And so let's group all the x's together. So I want to complete the square. So group all the x's together, the y's together, add 11 to both sides of your equation. Factor out a 9. Factor out a 4. And now let's complete the square. Okay, so 2 divided by, so the reason I factored out the 9 and all that is, and the 4 over here, is so that each of these quadratics are monic. So it makes completing the square a little easier. You would just take this coefficient and divide by 2, rather than having to take this coefficient and dividing by 9, the 18 and dividing by 2 times 9. So 2 divided by 2 is 1. 1 squared is 1. 9 times 1 is 9. Let's add 9 over here. Next. 4 divided by 2 is 2. 2 squared is 4. 4 times 4 is 16. 11 plus 9 plus 16 is 36. And so let's divide both sides of my equation by 36. So we get x plus 1 squared over 4, y plus 2 squared over 9 equals 1. So that's the equation of my ellipse. The center is at -1, -2. A in this case is 2. Square root of 4 is 2. B in this case is 3. Square root of 9 is 3. C, 9 minus 4 is 5. So C squared is 5. So C is equal to radical 5. Let's draw this. Since it was -2, okay. And then B was 3. Okay, that's fine. Okay, so, oops. Okay, so let's see. the center was at -1, -2. So let's do that. -1, -2. What the world? Okay, so here's the center. And we're going to go 2 in the X. And 3 in the Y. 1, 2, 3 in the Y. 1, 2, 3 in the Y. Okay. And so my ellipse should look something like this, more or less. And so the center is at -2, -1. My vertices are at, oh, maybe I should even say that here. So the vertice is at -1 plus or -2 -2. So it's at h plus or minus a k. And at -1, comma, -2 plus or minus b, which is 3. And the foci, b is bigger than a, so it's a -1, -2 plus or minus rad 11. Okay. And of course, you could calculate these, and that's what these are going to be. And so, oops. So this is going to be at 0 -1 and at 4 -1. And at -2, -4, and at -2, 2. Okay. And this will be along the y-axis. So this is square root of 11. It's around 3. Okay. Trying to move. It's not moving. Okay, so here it is. Wait. Square root of 5. Because square root of 3 didn't make any sense. A little bit bigger than 2. Okay, so there it is. A little bit bigger than 2. So the foci are at -1. Which is bigger? The 3 is bigger. Which is the B? Oh, that's why. I did this wrong. Oh, that's great. Okay. Sorry about that. Something was wrong. So it was wrong. Okay, so, and let's move it over a little. Okay. Okay. Actually, it doesn't have to be that big, but no, come on. Okay, so at -1, -2. That's the center. I had the center wrong. Okay, so that's, and then you go 2 in your x. So 1, 2 in the x. 1, 2 in the x. So the center is at -1, -2, and the vertex is at 1, -2 is at -3, -2. Oh, here it is. Yes. And that actually is what I got from this calculation. Okay, good. And let's go 3 in the 1, 2, 3. Okay. 1, 2, 3. Wait. 1, 2, 3. 1, 1, 2, 3. Okay, so here and here. So here's some more vertices are at -1, 1, and at -1, 5, which is plus and minus, which is actually corresponds to that. Good. Okay, so now that's correct. I was just checking, and that's the square root of 5. So you go a little bit over 2. So here, foci is at -1. This will be, well, rad 5 minus 2. And then this foci will be at -1, -2 minus rad 5. Okay, so let's try to draw this. If I can, best I can draw it. Okay, so there.